So good afternoon and welcome back to the class on tribology. So if you people remember in the last class, we were dealing related to the problems associated with hydrostatic journal bearing. So few were there into patentability presentation. So for those students, I just request you people to refer the YouTube link which has been shared related to the previous classes. But still, it is not a complicated issue. We had derived three equations basically. One is the load carrying capacity, the rate of oil flow, as well as the power loss. So these are only the three categories of the problems what you come across in solving the problem on hydrostatic bearings. So we solved around 4 numericals related to these equations, right? So it is a very simple problem. Everywhere they do ask just the supply pressure or the pressure across the oil inlets. So that is nothing but the P naught what you need to determine, and the flow rate is nothing but the Q and the power loss. So we basically use these three equations only. So this is for the rate of oil flow, what we have derived in the last to last class. So this equation you use to determine the rate of oil flow. And if you have any power loss, P naught, right? So then you need to have the equation for P, what we had derived earlier. So in this only, we have the equation for P value, right? So we will be using this equation to determine the value of the pressure within the inlet of the pipe. So this equation, and finally, we use the loss of power due to friction. So this was the equation we used to determine the loss of power. So those were neatly explained in the last class. So everywhere in the numerical, they provide the load value, the shaft speed, the shaft diameter, and the recess diameter, which is nothing but D1 and D2, and the film thickness and the viscosity of the lubricant will be given. So you will substitute and determine the answer. If they haven't asked to determine the supply pressure, if directly they have asked you to determine the flow rate, right? So to determine the flow rate also you need to know the value of P naught. For that you should calculate the power supply, sorry, the pressure supply. Okay, so this equation you should be very familiar. So they can sometimes ask to determine what is the pressure in the inlet of the oil, or else directly they can ask you to determine the rate of flow. So in both the cases, determination of the value of P naught is very much essential. So in this way, we solved like 4 numericals. So kindly refer the YouTube link for the last class, and I'll be sharing the PPT also shortly before your internals. So today we are going to move for the other part of our module 4. So I told you in the beginning, the module 4 comprises of 2 sections. So one is hydrostatic lubrication, the other one is the plain slider bearing with fixed or pivoted shoe. So we have covered the hydrostatic lubrication part, right? So similarly, now we have to focus on plain slider bearing. So associated with this, you should know what is the pressure distribution, what is the load carrying capacity of the plain slider bearing, and what are the losses of power you come across due to coefficient of friction and the frictional resistance which come basically in a plain slider bearing. And you have few numerical examples what you have to understand. So this part now we are supposed to focus on. So slider bearing is not a new concept to you people. So you have studied basically. So just a little bit few introduction concept before going. So the type of moment you get in any bearing, it could be either sliding or an rolling element, right? So these are the ways in which you will be having a relative motion. So based on the relative motion, you can categorize this into 3 basic types. So based on the ways of existence, they say direct straight torque on ways. So these are plain sliding or plain contact bearing, and other one is the rolling element, and the third one is the hydrostatic ways. So hydrostatic lubrication you have studied, and hydrostatic journal bearing you have studied. So that is one part. And the other part, when the relative motion comes into picture, it is the hydrodynamic bearing which come across. So hydrodynamic bearing and hydrodynamic lubrication aspects also you have focused, right? But we haven't spoken related to sliding moment, right? So here we are focusing on plane sliding bearing concepts. So what happens in case of plane sliding bearing concepts? So here the moving surfaces which are in contact will slide against each other. Even though they slide against each other, instead of rolling, a layer of lubricant is very much essential. Since the body is in relative moment and you are using a lubrication, it falls into the category of hydrodynamic bearing, not hydrostatic bearing. Hydrostatic bearing we have covered already. So this is the other part of hydrodynamic bearing, wherein we will be focusing on only sliding motion. So here the hydrodynamic bearing related to the sliding moment will be guided and controlled by means of the layer of lubricant what you are providing, right? So it again depends upon like what is the speed with which the sliding bearing is moving and what is the minimum amount of lubrication thickness is essential to slide effectively with reduced amount of wear and tear. So this is the straight talk away related to the relative motion which come across in between the contact area. So in this section, we are focusing directly on the sliding moment across the hydrodynamic bearing aspects. So this thing you have to keep it in mind. So before going for the pressure distribution concept, you should be knowing few general characteristics of the slider contact bearing. So when you hear the word either sliding bearing, yeah, plane sliding bearing, yeah, sliding contact bearing. So these are the very oldest and simple type of bearing technology which is there from many decades ago, right? Due to its existence from a long history, so it has found a wide range of applications, right from construction machineries to that of getting any resolution with respect to the automatic aspects. So like these are the range of applications in which the sliding contact bearings are in existence in our today's market. So with respect to that, when you think about a sliding contact bearing, you know that it utilizes the lubricant. Without a lubricant layer, it is difficult to perform any task in case of bearings. So this sliding contact bearing usually make use of different types of lubricants. And these lubricants again will get interface with that of the material. So we won't be knowing exactly what is the material with which the sliding contact bearing is made. So when you use a lubricant, so this lubricant layer will interface across the contact surfaces, right? So these contact surfaces are associated with the materials with which the sliding contact bearing is developed, right? So it depends how it interface. Any impurities are coming into picture. If any dopant is needed as an additive, right? So all those things has to be analyzed. For that purpose, it is always essential that you should check the range of lubricant which is feasible to run the sliding contact bearing very effectively. So you can try to evaluate the performance by using a very light oil to that of grease. Means you can vary the viscousness of the given lubricant and grade and check which yields the best optimum result for a smooth movement across all type of sliding contact bearings. So this thing, if you analyze, so then you can think about which grade of lubricant and which amount of viscosity is sufficient enough to run for a longer period of time, so that sliding contact bearing could be considered very much reliable for a long period of time. Apart from that, these sliding contact bearing are very robust in nature and they are highly reliable. I told you that because when you do the initial trial and error method, you will come to know which lubricant is the best. When you have optimized the selection of the lubricant, you can see that you have selected a proper lubricant, and hence it can run smoothly with reduced amount of friction, and hence you can claim it is highly reliable with respect to its robust in nature. So these are the other characteristics of sliding contact bearing. And lastly, what about the speed? So these have constraints on speed. So they are speed limited, and it have friction induced servo limits. Why it is speed limited? Because so it don't want to go for an higher extent where the friction will be induced for a higher range of values, and hence the design itself is constrained in such a way that it is not allowing a high amount of friction to be induced across a contact area. So this happens when it goes for a higher speed. So it has a limitation and a safe zone and a safe specific speed within which the sliding contact bearing could be run safely with reduced friction, and hence it is claimed to be as very reliable in nature. And apart from that, it is not too expensive, and hence it is not too expensive because it is the simplest type of sliding contact bearing, no complexion in designing and producing the unit, and hence it is very much economical, and it has already achieved many applications and grabbed the market, right? So this type of sliding contact bearing until now has not found any other replacement. So these are the very good and plus points of an sliding contact bearing, right? So before starting, it is just a general characteristics of how an sliding contact bearing looks like. So here you can see that you will be having an upper top surface which is called to be as a saddle. It will be made up of cast iron. So this could be placed over it. So you will be having a region in between. So this is a region for the linear actuator part, right? So here what happens, let me complete this part first. So you'll be having a saddle across the top, and now below you will be having the wipers. So this wipers will help in getting the compactness and getting the grip to be placed over the steel rails so that it can slide one above the other smoothly, right? So apart from that, when it moves smoothly, you should be having a layer of lubricant in order to reduce the amount of friction. So you have an oil distribution which is having in this section, because this is the most important part where while moving the friction comes into picture. So in this layer you will be having distribution of the oil. So wherein when it slides to and fro, the friction will be reduced and it will be very less. So you can use this type of sliding contact bearing for an longer run. So these are the main things what you have to understand. So you have gip pins here in between, and you have gip pre-hold bolts so that it will connect with the holes what you have over here, so it can be clamped easily, right? So these are the main important parts what you have in a sliding contact bearing. So when you have clamped this upper part on it, so it can smoothly slide one above the other. So these are the few general characteristics and information related to basic concepts about our sliding contact bearing. So lastly, you should know some advantages of sliding contact bearing. So mainly I have told you that it has a very less amount of friction which comes into picture because it has a constraint in speed, and hence friction will be very less. So when the friction is less, obviously the sliding contact bearing will be having a good resistance to wear, okay, and also the fatigue also, because it is not subjected to a continuous loading for a longer period of time. So it has good resistance to wear and fatigue. And also the material used in sliding contact bearing is such a way that it is not, it cannot get easily corroded, right? So the property of the material is not towards getting corrosion, and hence it has a good resistance to wear, fatigue, as well as the corrosion. And secondly, it has a very high sufficient strength in order to support the load which has been acting across the contact area. So this is the second plus point. And thirdly, it has a very fairly high melting point. Means the material what you use could be used for high temperature applications because the melting point of those material is comparatively higher. So due to this, it reduces the tendency for the generation of creep when sliding takes into picture. Since it has a high melting point, this type of sliding contact bearings are very much suitable for thermal properties. So wherein you can use at high temperatures and enable the heat which could be subjected during the process of formation of any relative motion. So these, like this, you have many plus points, right? And if you focus on metal to metal contact, so when you have a metal to metal contact, usually what happens is like there might be an option where it results in the formation of seizure, and also corrosion can come into picture across the contact of metal to metal also, right? So this type of variations which come across will not be seen if you select the material in such a way that it is free from all these types. So select a proper material, a good one, so that welding will be done very neatly. And it is a corrosive free material, right? And it is not focusing to the seizure type of wear which come across usually in other type of bearing material. So if you select the material a right choice, so when metal to metal come into contact, these things will not be seen. So that is one of the plus point of the sliding contact bearing. And the bearing, what they are using here is tolerant to dirt and foreign material. Sometimes what happens is the material, the sliding contact bearing is tolerant enough, but some other bearings, if they cannot, they even sense the dirt and the foreign material. So due to that, what happens that there will be like impurities across the contact area, which can result in formation of some barriers for the relative motion to come across the contact areas. But this is having a tolerant zone for the dirt and foreign materials, so that it will not be affecting the bearing very badly. And also the sliding contact bearing which are manufactured have the tolerance towards misalignment. So if any mild misalignment come into picture, it will not be providing a major drawback for the bearing. So this is one of the plus points. And this sliding contact bearing is made in such a way that it has a very good compatibility to the lubricant, right? So once you do a trial and error and do the optimization for the selection of lubricant, so rest all thing will go smoothly hand in hand for a longer period of time, and hence we can claim this type of bearing as a very reliable bearing with least amount of friction, and which has a very good resistance to wear, fatigue, and even for corrosion. So this is the beauty of sliding contact bearing, right? So what you have to know as a prerequisite before we start up with the pressure distribution. So you know that basically we have dealt with pressure distribution phenomena for all the type of bearings what we have studied, and we have calculated what is the load bearing capacity also, and what are the losses which come across due to friction, all those aspects. Similarly, here we need to focus, first understand about the pressure development, so then you can go for derivation of the equation. So first we are focusing on the mechanism of pressure development, which usually comes into picture across the parallel surface. Why we are using parallel surface? Because you need to see that this top surface is sliding on this. So you'll be having a contact area where you have two parallel surfaces. So when you have two parallel surfaces which slide against each other, what is the pressure which has been distributed due to the load subjection? So that you should be able to analyze. And hence we are starting up with study of pressure development across two parallel surfaces which are separated by an lubricant film, right, of a specific film thickness. So if we go for the diagram here, so you can consider two parallel surfaces. right? So this is the top and this is the bottom, or the two parallel surfaces, which is separated by a lubricant film. So H stands here for the lubricant film thickness or the oil film thickness, so that you are familiar enough, right? So this is the arrangement which has been done. And next you should see that the length of the plates is very long in the direction perpendicular to the plane of paper. So you should see that the length of the plates is assumed to be very long. If this is the length of the plane, plate 1 and plate 2, the length of the plate 1 and plate 2 is assumed to be very long. So this is one assumption we have to understand, such that it is in direction perpendicular to the plane of paper. So if you consider this as a plane of paper, so to this plane of paper, it will be exactly perpendicular and it will be in a longer length. So this is the basic assumption what you have to assume while drawing even the sketch. So let the length of the parallel plates will be comparatively long and show the thickness of the oil film in between these two plates. So these are the sections what we consider further, A dash and B dash. So I'll come to that a little bit later. So after drawing the plates and showing the direction, right? So you will ensure that the flow will take place in only one dimension. Even here the leakages are assumed to be nil for the oil film leakages, and hence the flow is considered in one dimension. It is not a two-dimensional one. If it is assumed in two dimension, the derivation still becomes longer. So in all the bearings what we have derived until now, the flow is assumed to be in one dimension only. Here also it is the same. So once you have kept these assumptions and aligned the plates in the direction perpendicular to the plane of paper, so now we should think about what is the velocity with which the upper plate is moving. So here you say that the upper plate is moving with a constant velocity u. So this is the upper plate. So it is moving with a constant velocity u. So at any time, if you check the velocity from here to here, or yeah, from here to here, yeah, from here to here, the velocity remains the same. So we are assuming that the upper plate is moving with a very constant velocity. And this is exactly parallel to the lower one. So this upper plate will be exactly parallel to the lower one. So that you have to understand. And later, it is seen that you will not be assuming any slip. So we assume that there is no slip happening when it slides against each other. So in that condition, so what we assume again is the velocity of the fluid is assumed to vary from 0 at the stationary surface to u at the moving surface. So this is the stationary surface and this is the moving surface. So this is sliding and it is moving with a constant velocity, right? So that is the thing what you have to understand, and it is assumed that the slipping is not been happening. So at no slip condition, you are assuming that the velocity of the fluid will vary from 0, means since it is stationary, the velocity will be 0, and as the sliding come across, so the relative motion, the relative velocity what you get will vary from 0 to the velocity with which it is moving across the upper plate surface. So here the velocity remains the same, but at the bottom the velocity will be 0. But as the layer of the fluid film will be moving, so the pressure gradient also will be different. We have studied the pressure gradient distribution in previous thing. Here also the same, slightly the velocity with which the fluid flow will be slightly increased. Here it will be 0, slightly you will get some velocity value here. Here it will be still higher, still higher, still higher, still higher, and here the velocity will be constant enough. So this is the thing what you have to understand, and this is the thing what we have assumed at a condition where no slip is happening. So you should all set right the assumptions very clearly, right? The plates are kept for a longer length in direction perpendicular to the plane, and the flow is assumed to be in single direction, so it is one dimensional. And it is third one is we assume that the upper plate is moving with constant velocity, and fourth one is we are assuming no slip condition wherein the velocity across the fixed plate will be 0 and it will be constant across the top surface, and the other layers of the fluid will be varying and it will be increasing. The velocity value will be increasing towards the moving plate. So these are the assumptions what you have to understand. Okay, so then if you draw two sections, A and A dash and B dash, you can evaluate what is the volume rate of flow of the fluid or the oil film across these two sections. And it has been assumed that the volume rate of flow across the section A dash and B dash will be the same, or it will be equal. So these are the things what you have to remember. Why it has been considered is because here the velocity distributions across the given oil film will be identical. So the distribution, velocity distribution will not vary. So wherever you go, again if you draw one more cross section here and take the velocity distribution triangle here, it will be the same. So it will be always same across any section what you take, because the pressure distribution across any section of the film of the oil will remain the same. Based on that theoretical aspect, we have assumed that the velocity distribution in this triangle will be equal to the velocity distribution in this triangle. It could be the same if you take one more section, C dash, and here also the velocity distribution will be film for the given fluid film thickness. Okay, so these all prerequisite concepts you should be very clear enough. Hope the things until now is clear. Any doubts? Any doubts? Are you people there?
Yes, sir.
Is it clear?
Yes, sir.
Okay. So this is the condition, the first condition, how the pressure distribution happens when you have one fixed plate and the other one is moving and both are parallel to each other. So next you should understand what will be the condition if one of the plate is inclined, how the distribution of pressure varies.
Good morning, ma'am.
Hello. Good afternoon. Yeah, please tell me. Someone told me good morning. What happened? Any doubts? If anything need to be told, kindly raise hand or you can unmute and speak. So this was for the first condition. Similarly, now we have to analyze how the pressure development and distribution varies when you have a convergent film. So you have one plate here where it is stationary and it is perpendicular to the plane of paper, whereas the other plate which was parallel initially, so now it has been inclined to some angle. So then you get a convergent film of oil towards the end. So here the thickness of the oil film will be different. What we specify it as H1, and here the thickness of the film will be different. What we specify it as H2. So when you have a variation in the oil film thickness due to the upper surface which has been inclined to the plane of paper instead of being perpendicular, so now you should understand how the distribution of pressure will be across the oil film. So that's what now we are going to discuss. So in this aspect, the sketch will be as shown over here. So here we are assuming three sections, A1, C1, sorry, A dash, C dash, and B dash, right? Why we took C dash? Because due to the inclination. So how the pressure is being varying, so that we have to analyze. For that purpose, we took this aspect. So here we have taken three sections. First, we will focus on A dash, and B dash. So here the velocity distribution at section A dash and B dash are assumed to vary linearly. So this is the assumption we are taking. So this is the section A dash, and this is the section B dash. Here the assumption is the velocity distribution of the oil film is assumed to vary linearly as it has been in an inclined position. It is varying in a linear way. It does not have any inclination with respect to the plane of plate which has been inclined. It is varying linearly only. The same assumption has been taken. And what about the velocity? So here again it has been assumed that it will be having a velocity of u across the moving surface. So this is the moving surface. Even though it is inclined, it is moving with the constant velocity of u. It is the same. And whereas at stationary, it will be 0. And as it moves towards the inclined moving surface, the velocity increases. So that is what being assumed over here. So at the stationary surface, it will be 0. At the moving surface, it will be u. And in between the stationary to moving, gradually the velocity varies linearly across the section A dash and B dash. So this is the entire area through which we are analyzing the pressure development, right, across the oil film. So these are the assumptions what they have done. So now, due to the variation of the velocity linearly, here we cannot assume that the flow is continuous. The flow is not continuous, and hence the continuity of the oil flow is not satisfied in the condition when the moving surface is inclined to some angle alpha. Okay, and hence you should be having something to understand more when it is not continuous. So what we do is we will assume that there is one more section C dash. Okay, so you will put in one more section C and C dash. Here also it is assumed that the velocity is varying linearly only, and hence in the velocity diagram you will show an linear variation with respect to the velocity. So this is the one more assumption which has been taken, right? So now, due to addition of one more section C dash, now we can assume that there is an continuity in the flow, and hence the flow continuity is being satisfied due to addition of one more section C dash. So once this has been satisfied, what we can claim is the velocity distributions at section B dash and A dash have to be given by the solid lines. What do you mean by this? Here we have just shown a profile with the dotted line. You can see here dotted line and dotted line, right? So if you have to prove that the velocity distribution is across the section A dash and B dash, velocity distribution have to be given by the solid line. If it has been displayed with the dotted line, that shows that there is no continuity, or the continuity of the flow is not satisfied, and hence it has to be shown that it is represented in continuous line. So if it is in dotted line, you have to assume that the flow is not satisfied. If it is in continuous line, then you can assume that the flow is satisfied. So these things are given for your understanding, and these could be used as a thumb rule, or you can consider that these are the basic assumptions what one has to think if you're designing an plane sliding bearing with having one surface inclined and one which is moving, another surface perpendicular to the plane of paper which will be held stationary. If you need to select this type of parallel plates for relative sliding moment, so these are the basic thumb rules and the assumptions what you have to understand before starting. So you should be carefully understandable in reading whether it has solid lines or not, right? So if there are solid lines, then you can assume or consider that the pressure buildup will be satisfied enough to bear the load and to check the amount of velocity induced to get the relative motion when it slides against each other. So if you have this type of film with the variation in its thickness from H1 to H2, so then we claim that to be as an convergent film. So this is the basic thing what you have to understand. So these are the basic concepts related to how a pressure will be developed if you have two parallel surfaces with one moving and one fixed, and what happens if you have two surfaces which is one inclined and one perpendicular to the plane of paper. So how the pressure distribution will happen. So if it is inclined, it will not be having a flow continuity satisfaction. So then we need to add one more section here and show that even the flow is moving, even the flow is linearly variable. So then if by chance, if in the design, if it is shown as a dotted line, then it proves that the flow of oil is not satisfied in continuity aspect. If you have a continuous line, then you can claim that the flow continuity is been satisfied. So these things you have to understand. So if it is satisfied, obviously it will be in the solid lines and not in the dotted lines. And once this is satisfied, obviously the pressure which is built across the film will be enough in order to bear the load and to slide properly with reduced amount of friction. But if in case the pressure is not built up properly, so that claims that the flow of oil is not continuous and it is not satisfied due to inclination of the moving surface. So that is ultimately the thing which comes into picture. So whenever the surfaces are parallel enough, you won't be having any problem. But when you have one inclined surface with respect to the moving one, you should be very careful in seeing that the flow continuity is satisfied always, irrespective of any angle of inclination of the moving surface. So this thing has to be very clear enough. Any doubts? Is it clear? Okay. So if that is the case, next we should go on in deriving the equation to determine the pressure distribution, the load bearing capacity, and the coefficient of friction which come across in an idealized plane bearing with an fixed shoe. So this is the next topic what you have in module 4 related to plane sliding bearing. So to come to this, you should be knowing what is the concept of pressure distribution. Without that, it is difficult to start up with this, right? So you should be knowing all the prerequisite concepts and the background related to the thing what you are studying. So this is a schematic sketch of a plane slider bearing, right? So here you can see you have again an inclined surface here, so wherein you will be having a short distance of the oil film which is claimed to be H2 and this is H1. So here the top surface is a moving surface which is moving relatively with a constant velocity, wherein the bottom surface here is inclined which is stationary. It could be in both the cases, either the upper part or the lower part. Anywhere when you have the inclination, the same concept what we studied will hold good. And hence we studied both the type of parallel surface, how it varies with respect to the pressure distribution. Fine. So here will be H1 and this will be H2, right? And this is the fixed one and this is a moving surface and this is the length, the width, and this is the length of the moving surface. So with this aspect, we have to start up with the hydrodynamic plane slider bearing. Even though if they tell you plane slider bearing, one thing you remember, it is an hydrodynamic type and it is not a hydrostatic one. So after seeing the sketch, you can tell that a hydrodynamic plane slider bearing is usually made up of two planes. As you saw in the sketch, it is usually made up of two planes, right? So it is not parallel to each other. It is non-parallel. Why it is non-parallel? You have two surfaces which are not parallel to each other. If the fixed surface was in this direction, perpendicular to plane of paper, then you would have claimed that both the surfaces are parallel. Since it is inclined, it is a non-parallel surface which has been separated by a lubricant film. So obviously you'll be having a lubricant film. So it has been separated by a lubricant film. So the thickness of the lubricant film here is H1 and the thickness of the lubricant film here is H2. So likewise, the film thickness varies from this point to this. So this is the width of the surface, top surface, and this is the length of the top surface. So this is the initial arrangement. So next, here what is the assumption is one of the surface is normally held stationary while the other moves with a constant speed. The same thing. I explained you how the pressure distribution happens, right? So even also here, even though the moving surface is inclined, it will move with a constant velocity here, right? Similarly, now here in pressure distribution type of plane slider bearing as well, we assume the same thing, that the surface which is normally stationary, one surface will be normally stationary and the other surface will be moving in a constant speed. So this is our moving surface and this is the fixed surface. So this moving surface will be moving constantly with a constant velocity. So it will not change. It will be a constant value right from this corner to this, right? So that is the thing what you have to keep in mind. And after that, the direction of motion and the inclinations are given in such a way that a converged film is formed. So now we should show the direction of motion how it is. So we'll show the direction of motion in such a way that a converged film is formed. A converged film will be formed due to the inclined stationary plane. But still the direction of motion is in this way so that you can get a converged way for the flow of oil film. So that is what being told over here. And next we are speaking about the stationary plane. How the stationary plane could be. So the stationary plane could be either be fixed or pivoted. So both the things will hold good. The stationary plane could be totally fixed or it could be pivoted. Why? Because it can be assumed that any inclination what you get will be relative to the moving plane. So once it is fixed, pivoted, constrained at particular degree of freedom, so it will get the relative motion based on the movement the moving surface is moving, because it will not be having any velocity here because this plate is stationary. It is fixed or it is pivoted. Only this surface will be moving. So due to this, the relative motion will be coming and it will be maximum across the top layer and it will be minimum across the bottom surface. So it gets relative motion with respect to the moving surface only if it is fixed or pivoted. So due to that reason, you will see that the stationary surface could be either fixed or pivoted so that it gets relatively velocity higher at the top and least at the bottom. So this is the thing what we again assume, okay? So once this initial conditions are cleared enough, so then we should start up with determining what is the hydrodynamic pressure, what is the load carrying capacity, and what is the frictional force and coefficient of fluid friction which come across in an plane slider bearing, right? So these three parameters have to be derived by using the concept of pressure distribution what we studied. So this is nothing but the mechanism of the pressure distribution, so which come across the given hydraulic oil film. So it could be parallel or it could be converged. So in both the cases, we can try to extract the derivation part. Okay, so it is a huge derivation which shows all the three. Sometimes it could be asked, even though it is big, we cannot think that they won't ask in the examination. If you're lucky enough, you can get the numericals, or sometimes they can ask you to derive the load carrying capacity. right? Or else what is the pressure distribution? Sometimes both they ask the pressure distribution equation as well as the load carrying capacity. So you should be able to derive. So if you derive, you will get full marks, right? So to derive, before going for derivation, one more thing what you have to assume here is, for all idealized plane slider bearing, so no variation of pressure will be assumed in the direction Z. So this is one more assumption what you take. So this is the Z direction. So no variation in the pressure will come across in this direction. So this is the assumption which has been made. Okay, so that has to be considered. So keeping that assumption in mind, we start doing the differentiation with respect to the Reynolds equation. So we have derived the Reynolds equation for one-dimensional and two-dimensional, right? So we will be going with using the Reynolds equation, and we start up the derivation. So now it is 12:43. So if I start up with the derivation, I won't be able to complete. So tomorrow morning we will start up and complete the derivation of plane slider bearing. So kindly don't miss the class. All of you do attend the class. So if you have any doubts now related to all the concepts of plane slider bearing, so kindly let me know. Parallelly, I will take the attendance. Any doubts associated with the concepts of plane slider bearing? Any doubts, student? If any doubts, please kindly let me know. So everyone can type your name and USN in the chat room. I will call the attendance parallelly. Abdul Khalik Pasha. Abdul Khalik Pasha is not there. Akil KV.
Yes, ma'am.
Alok M. Alok is again absent. Ankesh Aman.
Ma'am, Anil ma'am.
Yeah, Anil Kumar. Ankesh Aman. Ankesh is absent for 2 classes continuously. I don't know why. Gautam Krishna. Gautam Krishna is also absent. Balaji VR.
Present, ma'am.
Beldar Mohammed.
Yes, ma'am.
Chaitanya.
Present, ma'am.
Chetan Kumar. Chetan absent. Dheeraj.
Yes, ma'am.
Ishant.
Yes, ma'am.
Harshit. Harshit. Himanka. Himanka is also absent. Kanishka.
Yes, ma'am.
Nagamurli Krishna. Nagamurli Krishna absent. Kunal Raj.
Present, ma'am.
Danush is not there. Mohammedayan. Mohammedayan is absent. Mohammad Junaid absent. Shri Prasad.
Yes, ma'am.
Niharika. Niharika absent. Nihar.
Yes, ma'am.
Nikhil.
Yes, ma'am.
Nirab.
Yes, ma'am.
Prajwal S. Bhatt.
Present, ma'am.
Rishabh Pandey.
Present, ma'am.
Rohan. Rohan Kaglakar absent. Roshan Yadav. Roshan absent. Sumant Sagar.
Yes, ma'am.
Sagar Dutt Mathur.
Yes, ma'am.
Sagar GV.
Present, ma'am.
Sanjay Raghav.
Present, ma'am.
Okay. Shobit.
Present, ma'am.
Siddharth B.
Present, ma'am.
Raj Sridhar.
Yes, ma'am.
Subramanya.
Present, ma'am.
Tidumana Sethi Rohan.
Yes, ma'am.
Okay. Ullas. Ullas. Absent. Vidyan. Vidyan, you're there? Varun.
Yes, ma'am.
Pavan.
Present, ma'am.
Danush.
Ma'am, present, ma'am.
Dhyanesh.
Yes, ma'am.
Gunasagar.
Present, ma'am.
Meghanatha.
Present, ma'am.
Rasik Baran.
Present, ma'am.
Shiv Krishna.
Present, ma'am.
Shreyas. Shreyas. Absent. Srinivasalu. Srinivasalu. Okay. Yogananda.
Present, ma'am.
Kiran R.
Yes, ma'am.
Ranveer Singh Chauhan.
Present, ma'am.
Gautam Sai.
Present, ma'am.
Ranveer, kindly be regular. Yours is the 11th class on 33. I know you have given the medical certificate. In future, kindly be safe.
Yes, ma'am.
Shiv Pavan. Shiv Pavan.
Present, ma'am.
Okay. Alok, I'm calling again. Are you there? Alok and Abdul Khalid
Ma'am,
Pacha.
Abdul, ma'am.
Ma'am,
Yes,
roll
Where,
ma'am.
number
I'm here, ma'am. Abdul, present, ma'am.
where you were when I
Abdul,
called my
present,
name?
ma'am.
I think you have joined now then.
I'm sorry, ma'am. Ma'am, no, ma'am.
The-
Actually, I didn't unmute my mic.
Even your classes attendance is very low. It is 18th class on 33. Kindly do attend
Mine,
regularly.
ma'am. Abdul.
Yeah, Abdul Khalid Pasha.
Ma'am, roll number 29,
Okay.
ma'am.
Alok is there? He's
No, ma'am,
absent.
roll number 29, Mohammed Junaid.
Mohammad Junaid. I called your name, no?
Ma'am, I couldn't answer because of the internet connection, ma'am.
Mohammad Junaid. Okay, I have given the
Excuse
attendance.
me, ma'am.
Okay,
Yes.
thank you.
Yeah.
Ma'am, any news about the internals, ma'am?
Yeah, the internals as per calendar of events, it is mentioned on 7th.
Is it going to be on 7th only, ma'am?
Why, what happened? Why this question has arisen?
To prepare, ma'am. Either we do that or we can focus on our project.
No. You do both actually. As per COE, it is that, and we have some open day for third and fifth semester. So first day is on 4th and the second day is on 7th. So until now, we haven't received any change in the internal date. If that is not done, I think it has to be on the same dates. But still, if you have a doubt, I can clarify and let you know later.
Yes, ma'am. Can you please let us know?
Yeah, I will do that and inform you. But you please
Okay.
attend the classes regularly first, Kanishka.
Yes, ma'am.
Okay. Fine then. Take care. Have a nice day.
Thank you, ma'am.
Thank you. Bye-bye. Yeah.